Fusion, the process that powers the Sun and other stars, holds the promise of providing a clean, safe, and virtually limitless source of energy here on Earth. The release of energy in fusion reactions arises from the intricate interplay of subatomic particles, and the conversion of mass into energy, as described by Einstein's famous equation, E=mc². Understanding how fusion produces energy requires delving into the intricate world of atomic nuclei, their interactions, and the principles of nuclear physics. At the heart of fusion lies the phenomenon of atomic nuclei coming together to form a new, heavier nucleus. This process is governed by the strong nuclear force, one of the fundamental forces of nature, which binds protons and neutrons together within the atomic nucleus. In stars like the Sun, the high temperatures and pressures in their cores create an environment where fusion reactions occur, releasing a colossal amount of energy in the form of light and heat. The fusion process begins with hydrogen nuclei, also known as protons. The simplest fusion reaction involves the fusion of two protons to form a helium-2 nucleus, also known as a diproton, along with the emission of positrons and neutrinos. However, this reaction is extremely rare due to the inherent repulsion between positively charged protons. To overcome this repulsion, extremely high temperatures and pressures are required, such as those found in the core of a star. In stars, fusion primarily involves the fusion of protons to form helium nuclei, a process known as hydrogen fusion or hydrogen burning. This process releases an incredible amount of energy through a series of steps. The most common fusion reaction in stars is the proton-proton chain, which involves a multi-step process resulting in the formation of helium for nuclei, positrons, neutrinos, and energy in the form of gamma rays. On Earth, replicating the extreme conditions required for natural fusion reactions is a significant challenge. The most promising approach is using isotopes of hydrogen, specifically deuterium and tritium, in a controlled environment called a fusion reactor. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron, while tritium has 1 proton and 2 neutrons. These isotopes are chosen because their fusion reactions release more energy, and require lower temperatures and pressures compared to natural proton-proton fusion. In a fusion reactor, the isotopes of hydrogen are heated to extremely high temperatures, on the order of millions of degrees Celsius. These temperatures are so intense that they cause the isotopes to exist in a plasma state, a hot, electrically charged gas. This plasma is confined using powerful magnetic fields or intense laser beams to prevent it from coming into contact with the walls of the reactor, which would cool and disrupt the fusion process. When the plasma reaches the required temperature and density, fusion reactions between deuterium and tritium nuclei become more frequent. The primary fusion reaction involves the fusion of 1 deuterium nucleus and 1 tritium nucleus to form a helium nucleus, a neutron, and a substantial amount of energy. The energy is carried by the kinetic energy of the products and, most importantly, by the kinetic energy of the ejected neutron. The energy released in a fusion reaction arises from the difference in mass between the reactants, deuterium and tritium nuclei, and the products, helium nucleus and neutron. According to Einstein's equation, E=mc², this mass difference is converted into energy. While the change in mass is incredibly small on an atomic scale, when multiplied by the speed of light squared, c², it results in a significant release of energy. The challenge in achieving practical fusion power lies in controlling and sustaining the extreme conditions required for fusion reactions. Since fusion reactors are dealing with temperatures hotter than the core of the Sun, containing the plasma becomes a formidable task. Various fusion approaches, such as magnetic confinement, tokamaks, and inertial confinement, laser fusion, aim to achieve these conditions and harness the resulting energy for practical applications. In conclusion, fusion is a process that releases energy through the fusion of atomic nuclei, resulting in the conversion of mass into energy as described by Einstein's equation, E=mc². In stars, the intense temperatures and pressures in their cores enable fusion reactions to occur, producing the light and heat that sustain these celestial bodies. On Earth, harnessing fusion energy requires replicating these extreme conditions in a controlled environment. While achieving practical fusion power remains a complex challenge, the potential benefits of a clean, safe, and virtually limitless energy source drive ongoing research and innovation in the field of fusion science and technology.
Guys, I hope you liked this video. If you like this video, please share this video with your friends and family members for more information. And please press the bell icon and subscribe my channel.